actually the matrix representation of this more complicated Hamiltonian in a very small subspace. Okay, and then we can use this equation of motion to figure out how the density operator should evolve. So is this procedure clear? Okay, this is usually used to analyze many other two-level quantum systems as well. Okay. And actually, the rho bar is just the matrix elements of the two-level system. And if you describe the two-level system with this thing, we actually figure out what this was earlier, and then from this we can actually figure out the matrix elements. I'm going to not distinguish between rho double bar and rho hat. I think of them as the same thing, just like here. I would not distinguish between the matrices and the real operator. I'm going to confuse these two, and I hope that you know what it means. Okay, this is just equal to, if I were to pick out the diagonal and off-diagonal elements from there, it will be just A1, A2 conjugate, A2, A1 conjugate, A2 squared. You'll find that the density matrix is just given by that for this two-level system as such. Those are the coefficients of the density operator. And we assume that each atom can be described by that two-level system. Okay? And we use that to describe each atom in the example. And now you can find the equation of motion. That is slightly harder. Okay, I'm not going to distinguish between matrices and operators. Okay, I'm going to confuse the notation and say that this is just equal to that. As I've shown you before, it doesn't matter. You can replace all the hats with double bars, which means matrices in this equation still hold true. And then you work out this detail, and then you plug it in and find the equations of motion. I don't know if I should go through the details with you, but I can go through the rough idea of the details. So I have rho had been equal to rho 1, 1, rho 1, 2, rho 2, 1, rho 2, 2. And then you plug that into this Hamiltonian and multiply things out. And then you would have the rho hat dt is equal to I h bar, rho hat h hat minus h hat, rho hat. Okay? And then the others is just lots of details, okay? Rho 1, 1, rho 1, 2, rho 2, 1, rho 2, 2, and then you just plug in the Hamiltonian, the subspace projected Hamiltonian. And then we do the same thing for h hat, rho hat. Rho 1, 1, rho 1, 2, rho 2, 1, rho 2, 2. And then you just multiply things out to get the equation of motion. Okay? And I won't multiply everything out, but just tell you the answer. Okay? If you identify the top left element, you will multiply this with that, and this with that. You can see that some of the terms actually cancel. E1, rho 1, 1, E1, rho 1, 1 will cancel each other. Okay? You multiply. But rho 1, 2 times this one, if you try to construct this element over here, and then this one times that one, they don't cancel each other. This is rho 1, 2, E2, and then rho 2, 1, EU1. So this is rho 1, 2, this is rho 2, 1. So they don't cancel each other. So the elements that don't cancel each other, for the top left element is left with rho 1, 2 minus rho 2, 1. So the top left corner is left with just the off-diagonal terms. The diagonal terms actually cancel each other, which is reasonable because the diagonal terms represent the unperturbed Hamiltonian. And in that case, the equation of motion should be constant because those are stationary states. They don't change with time. It's only when we perturb the system that we get this off-diagonal terms. This off-diagonal terms is going to cause an interaction between the two levels. And there will be time evolution. Okay? So you see that the off-diagonal terms are contributing to the time evolution. And then this is the electric field that we put in the system. This is the electric field that we put in the system. That is also causing the system to change. And then the other one, if you look at the other term, which is this thing over here, it should be this thing times this thing, minus this thing times that thing. Again, that some terms are cancelled, and what is left behind is just the term that is contribution from the electric field. If the electric field is not there, this term would not have been there. And then you will have E2 minus E1 times rho 1, 2. Okay. And then this other term is there because of the presence of the electric field. This term is there because rho 1, 2 is not equal to 0. What is rho 1, 2? Rho 1, 2 is just this term over here. Okay. If the two levels are entirely uncorrelated, this would have been 0. If level 1 and level 2 of the quantum system has been uncorrelated, this would have been 0. Okay, but because there's some coherence between the two levels. So if the quantum system is jumping between the two levels, if there's coherence between them, it contributes to this term. This term is proportional to the energy level difference and then the coherence between the two levels. Okay, and then you have the other terms, which is very similar to that. One due to the presence of the electric field, rho 2, 2 minus rho 1, 1, plus E1 minus E2, rho 2, 1. Okay, the off-diagonal terms. And then the diagonal term, again, that is coming from the presence of the electric field, rho 1, 2 minus rho 2, 1. Okay. The electric field is causing the levels to jump, the atom to switch from level 1 to level 2. So there is some sort of a coherence between the two levels. So rho 1, 2 cannot be 0 because they are all been excited by the same electric field. There's some kind of a coherence between them. So now you have the equation of motion for the density operator given by this. This is just equal to the rho hat dt. And we can actually look at it element by element. We look at it element by element. And you will find that if you look at it element by element, then the off-diagonal element, which is the correlation term, the off-diagonal element is a correlation term between the two levels, okay, is proportional to the density difference. This is like the density difference between the two levels. Okay, how many atoms, how likely the atom is going to be level 1, how likely the atom is going to be in level 2. So this is like the probability density of the difference times the electric field, okay, minus the coherence term, rho 2, 1. And I can write this as being equal to, this is some sort of a frequency, so I can write this as minus I omega 2, 1, rho 2, 1, plus I mu b over h bar delta rho. Delta rho is like the difference between the probability density. So the rate of change of the off-diagonal term is given by this. Okay, this is, if this term is not there, then it says that there is a chance of correlation between the two. This is like a resonance behavior, okay, between level 1 and level 2. And the presence of the electric field is going to make a difference. There should be an E here. Okay, this is like the driving term from the electric field. We'll go more into this next time. Okay, actually I can write down the equation of motion for rho 1, 1 as well. The density, probability density for level 1. It says that the probability density for level 1 would not have changed if there's no electric field present. Okay, if the atom is in state 1, it remains to be in state 1 without change. However, if there's a presence of an electric field, okay, the electric field will push for a change of this, and it's the difference between the correlations between the two states. Okay, and then you can find d rho 2 dt also will be given by something very similar. The electric field pushes the state to flip-flop between the two states, and then it's given by that. Okay, these are the equations of motion for the off-diagonal term. The one for rho 1 is very similar. This is for the diagonal term. We will solve this equation to see how the interaction of light with a cluster of atoms give rise to effective dielectric constants, and so on, give rise to resonance behavior that is quite useful in describing lasers. Okay, we'll stop here and continue next time. It can also be used to describe a spin system like NMR, MRI. You can also use this kind of equations to describe MRI and NMR. Yes?
Are those both rho 1, 2, and 2 with the time?
Over here?
Yeah.
Is rho 1, 2 and rho 2, 1, right?
Both diagonals, because here it's
Rho 1, 2, rho 2, 1, right? Rho 1, 1, rho 2, 2, right? Sorry, this is rho 2, 2. Let me see if I get anything wrong. You can look at the